So today our topic will be the quantum dilogarithm, but this time as a complex function. So today we will be heavy in complex analysis. So the problem of quantum dilogarithms is that most of the properties analytic aspects are all done in physics papers. So mathematically there aren't that many rigorous proof written down. So I have to credit my master students who provided most of the proofs in rigorous details, especially on this contour integration. You have to really prove things converge and tends to zero and all this stuff. So most of the details in this talk is provided by my students, so I have to credit him. So let's just recall our definition. So our our quantum dilogarithm yesterday is defined as the following infinite product. So this is an infinite product of the following type. Right. So as a complex function, so z is complex, then this thing will converge provided that q is less than 1, and it converges to a meromorphic function. So it is a nice complex thing, infinitely differentiable, except at the poles, except where the denominator is 0. And we also learned yesterday that this can also be written down as a infinite power series. And this power series converge also as a complex function, provided that C is inside the radius of convergence. Yeah. And finally, too big. And we have also the asymptotic behavior that tells your relationship with the standard Euler's dilogarithm. So, so as a complex function, it's just a number. So when q goes to 1 from the left, so q is real, and goes to 1 from the left, then this function behaves just like the Euler's quantum dialog. Yeah, so that's basically what that's all about the version we used yesterday. Now the problem is what happens when I take my quantum parameter to have norm 1 instead of less than 1. Then, well, very quickly you can see that the infinite product is really bad. It just diverge and fluctuating a lot and in a very crazy behavior. So this function basically does not make any sense when q has norm 1. But amazingly, the discovery probably by Fadiev is that instead of one single function, you should also consider another copy in the following sense. I should use this symbol. Something like that, maybe. Yeah, so his idea is that instead of one copy, you should take in 2 copies. So here, if I parameterize q as pi I b squared, so and q tilde is e to the pi I b minus 2. So of course, if b is real, this is norm 1, and this does not make sense. But if the b is taken to be some complex number satisfying imaginary part of b squared bigger than 0, then this will imply that both Q and minus. Then I should use minus here. Both Q and Q tilde will be less than 1. So if I take b squared imaginary part to be bigger than 0, then both of these number has norm less than 1. And this makes sense. This converge. And c tilde here is something like formally 1 for b squared. And we'll explain this more. Yeah, so both things converge, and it turns out that it converged to some nice function that can be analytically continued back to the case when B is real. So this gives the so-called non-compact version of the quantum dialog. So non-compact quantum dialog corresponds to the case when Q norm is 1. And also additionally, that if you move Q away from this unit circle, you recover a ratio of 2 dialogues. Yeah, so that's kind of the plan of today's talk, is to understand precisely what this means. So give it a name. So I'll use phi and b for this b here. Yeah, so we'll instead define the function directly first, and then show that it equals this ratio. So the setup, we start with a complex b, and we assume the real part of b is not 0. And this is some constant that appears again and again in this talk. So I'll give it a short-term name, CB, common integer. And then Q is IB square Q to the. And sometimes you want to remove the sign, so we should check to denote the minus, to denote the one without sign. So short form. Okay. Right. So the phi dx quantum dialog. So I'll use again the term non-compact to distinguish it from the compact one we did yesterday. So phi dx quantum dialog is defined as follows. So for any complex numbers such that it lies in some strips on the complex plane. So this is a condition for convergence. Then it is defined as follows. So it's exponential of minus 1/4 of an integration. I have to be careful here. Okay. So this is the expression where you have an integration, and this integration is a contour integration. So contour integration in terms of complex integration. So it goes along the real axis. So this is the real axis. So it goes along. It goes along the real line, and then you can see that there are poles on the integration. So you have division by 0 downstairs. So there's a pole at 0. So the contour will just go over the poles in a small semicircle. So this is my contour. So it is along the real axis, except that around the x equals 0, you go above it. And since it is a contour integral, and also everything is analytic, you have exponential, you have sine, hypersine. It's just e to the c. Right. So you have hypersine, they are analytic. These are analytic, exponential, everything's analytic. So this thing is good as analytic integration. So it does not really matter how big this semicircle is. You can adjust the size. The value of the integration does not change. Of course, you cannot like make it too big and pass through other poles. Like small enough semicircle. Yeah, so that's the definition as a complex function, and one can show that it depends analytically on B and C. Again, because everything is just defined by exponential. So there are first two simple observations. Oh, yeah, and also like the conditions there, imaginary C less than imaginary CB, will guarantee that this thing converge as C goes on both sides of infinity. So you can just look at the sign H. There's an exponential decay, and you can check that that condition corresponds to the exponential decay on the axis. Yeah, so the integration is well defined. It converges to a finite number, except at several places. And yeah, you have this. So the first very simple observation is that there are some symmetry in the B parameter. just replace B by B inverse or B by minus B. So this is kind of like a trivial trivial statement. So but there already gives you some important aspect of the function, is that there's this kind of modular symmetry. Well, which is probably one of the main motivations for introducing this function in conformal field theory, because this kind of B inverse thing appears as the symmetry in the central charge of the field theory. Yeah, so everything we work out will more or less have this kind of B inverse symmetry everywhere. Another important properties that is more useful next talk is the unitarity. And let's just say unitarity. I don't know what's the correct now. So if B is real, or the norm of B is 1, then, well, this is a complex number. So you can take the complex conjugation. And if you take the complex conjugation, it equals its inverse with the complex conjugation on the argument. So you have this relationship between the complex conjugation. And in particular, you can see that if Z is real, then the norm of this complex number is 1. Right. So if C is real, then this is the bar is gone. So it's phi bar is 1. So the norm is 1. And this is particularly important because later in the third lecture, we'll see that because of the size 1, if I plug in any like self-adjoint operators inside here, I will obtain a unitary operator in terms of functional calculus. So this is one of the very important properties that will be very useful next talk. But I'll first state here. Yeah, very important. It's very important in functional calculus. So we don't need this anymore. Oh, actually, I want to keep both. Never mind. Right. So now we'll basically prove this statement. Just right here. So this C is not that C actually. It's more or less an idea. So I'll just write it here. So if b squared is bigger than 0 and the real part of b is bigger than 0, then I have this formula, but I have to change the argument. Should be the exponential of that. Sorry. Yeah, so that's the correct thing. Right. So the theorem is that we define our function. This is for arbitrary b, arbitrary complex b, where the real part is not 0. Then when we look at the range when b satisfies this region, we actually can rewrite the phi b in terms of ratios of two compact versions of the dialog. Yeah, and one remark is that here I have to assume real b is bigger than 0. I have this kind of symmetry here. So if I know the case for real b bigger than 0, I will know the case for real b less than 0. I will also know the case for imaginary b squared less than 0. So really, we just need to focus on this range to understand the full behavior. And actually, if you look at the literature, many people don't write this line, which will be wrong. Because if they don't assume real b is bigger than 0, then it will depend on whether the b is negative or positive to have extra signs here. And some literatures just missed out this part. Yeah. So we'll focus on this case. And as I said, when imaginary b squared bigger than 0, both q bar is less than 1. So the ratio on the right-hand side makes sense. And so to prove this kind of relation, the usual techniques from complex analysis states that if you have two analytic functions that coincide on the same domain, on some domain, then they will be the same on the whole complex. So this is the analytic continuation theorem. Well, I mean, usually on some domain here, I mean, for example, it contains some open set. But we also know that it can be more general, like if it has some limit points, then it's already okay. So if they coincide on a set that has a limit point, then the two functions has to be the same on the whole complex plane. So yes. Yeah. Now it's equality. I think Fadiev defined this, but we used that as our definition. So now this is the equality. Yes. Make sure the logic is correct. Okay, yes. So historically, his idea is to take the ratio first, but then we know both expressions are the same thing. So we define phi b that way, and we prove it is a ratio, right? Yeah. So if two functions are analytic on some domain, then they're the same on the whole thing. So we know both functions are analytic. So we just have to show that they coincide for some good choice of z, right? And we will just take c to be like negative enough, for example, to make sure that both sides converge. And of course, then the proof is the proof of the theorem is by residue theorem. Well, because phi is a integration, and we can evaluate complex integration using residue theorem by encircling the whole function with a big contour and then find the poles in an appropriate region. Yeah. So first observation is that both poles, what are the poles? Right. So I have n pi I, this one, and this one. So first of all, I have the poles from the sine h function. So if you plug this into the sine h function, it becomes 0. So these are the poles for sine h function. And because we assume that the imaginary b squared is bigger than 0, these are actually simple. So they do not coincide. So these are all simple poles. So these are simple poles because BB inverse are linearly independent due to the assumption. Well, there's also one more pole. We also have x equals 0. And this is a triple pole. So there are 3 zeros on the bottom. So these are the main poles for the integration. And our contour really avoids the triple pole thing, so we can ignore the x equals 0. And we want to choose the contour so that it goes above the complex plane, so we can ignore the things below. Yeah, so we have poles, then we can calculate the residue. So the residue at this point is -1 and okay. You have this, and for the B inverse, you have the B inverse version. All right. Just the B inverse version. Yeah, so residue as in complex function, I hope everyone knows how to compute residues. Yeah, so we will take the following contour. So the bottom part is the red one. And we basically encircle it with a big semicircle on top. So if I choose this contour, then it corresponds to, of course, the case n and bigger than 0. So I'm just looking at the poles where the n and m are positive. Yeah, so it will look something like this. I mean, B is complex, so B may not be real, so somehow slanted. Yeah, so if I compute the integration of this, then by the residue theorem, it means that I'm looking at the summation of the residues of the things inside, which means I'm looking at summation of these terms. Oh. So after simplification, you get this for the n, and then the m, which I use n. Okay. So I got this. And we have the assumption that QQ inverse is less than 1. So this can be rewritten as infinite sum also. Yeah, so this can be written as infinite sum. And similarly for this one. And so now the next step is that I have two summations. So just like yesterday, I have two summations. I will try to interchange them. And so to make sure that everything converge, we can, for example, let C to be the complex number such that the real part is negative enough, so super negative, and also in the region where if you multiply C by this complex B or B inverse, the real part is also negative. So this is the domain that we are required for both sides to converge. So if you take in this range, take in the fact that Q is less than, Q and Q theta is less than 1, then we can interchange the summation and we can evaluate them in terms of a log. So summation over here will be set to n will become like the log. So the end result will be 4 times minus 4. And you can see that this is exactly the log of psi q and psi q tilde. This is the infinite product of that part, which is the 1 over psi. And this is the infinite product of the 1 over of the psi q tilde part. So this becomes like the log of the psi and psi. 4 times. So the 4, 4 times the 4 cancels with the 4 there. And the minus also. So I should put this. So minus 1/4 of that is that. So this is the contour integral, but of course, rigorously, we have to also show that the integration of the outer semicircle goes to 0. And the details are what I claim is written by my students. So, but I will go into that detail. So I'll just claim that the semicircle will goes to 0 as R goes to 0. So just by reparametrizing the contour with, say, R sine theta.
R goes to infinity?
Of course. You know, when I type LaTeX, I use /00 to denote infinity. very convenient.
The summation in the third term in the
Oh,
last line.
This one?
No, the last line. For a log.
Thanks. So there's some kind of estimation of the size of the contour, the length of the contour, and well, actually the function is not that bad. It's all exponential in sign, so it can be done. So what we have shown here is that in the contour integration, the outer semicircle is gone. The real line integrates to the ratio of psi over this open domain. So the two functions coincide in this open domain. So by analytic continuation, it matches for the whole region. And that's the proof. And so with this, we can state some more properties of the quantum dialog. Yes?
Your expression is something with the inverse of other discovery.
Inverse.
Yeah, converse of discovery. Is it possible to find such a kind of expression?
Yeah, so it comes from the functional equation I'm going to say, I think. And this basically just trying to find the matching summation, matching residues to add up to the poles. So it's probably going from this way up.
Is it kind of something the iterated integral expression?
This sorry.
Iterated integral.
No, it's just a single.
Usual dialog is iterated integral. Usual dialog can be written as a iterated integral.
Oh, that I don't know. That I don't know. But at least in the Fatier's first paper, he has a functional equation, and he said, "Okay, this is the solution," before explaining where he comes from. But I mean, if because it flows from a functional equation of psi. I'm going to write down. And then probably if you go back up this way, you can recover which function requires you to get to this possible pole.
So he solved that equation.
I think
get that.
so.
Okay. There's a question.
Yes. Yeah, there are two series of poles. It's not the poles of phi. It's the poles of this integration. We are talking about the poles of this integration, so it's only from sine h, and x. No, I'm going to talk about that. Not yet. Right now, the calculation is only for the integration of that elementary function, which is the sine, and x. Nothing else. Yes. Yeah, so now we know that phi and psi are the same for that region. Then we can write down the functional equation satisfied by it. So there are two lines. One corresponds to B, one corresponds to B inverse. I think I use the check version. So we have this functional equation, and well, we know the psi, recall the psi satisfies similar thing. So it satisfies Q squared C equals right. So the psi satisfies this, so the ratio of psi's will satisfy a similar thing, where when you shift by bi, say when you shift by bi, the bottom argument is like 2 pi c, 2 pi I. It becomes 2 pi I, so it vanishes. So if you look at the first line, only the top psi gives you the corresponding term here. And so this equation holds when imaginary b squared is positive. So you can turn this into psi, take the functional equation, and goes back to phi. But then because both sides are analytic in B, you can remove the requirement that imaginary b squared is bigger than 0. So the general B case follows from analytic continuation. And as I said, if you change B to -0, less than 0, then again you should have some additional signs floating around. Yes.
That equation has unique. The solution is unique.
This one?
That function equation.
So the argument is that phi b of this equals the ratio of psi.
Yeah.
And using the functional equation, it equals the ratio of this times an extra term, and then goes back to this.
But the yellow equation has a unique solution.
I mean, it depends on the initial condition, of course. But we know the psi one satisfies this.
It seems like the monodromy equation.
This is as power series. This equation is a power series, yes. Yeah, so you have, we have this argument yesterday, and we are just taking phi equals that, equals that. Yeah, it might not be, it's unique up to some initial conditions. Just a single equation. Yeah, so this also explains why I think it's one of the reasons it's called double gamma, but probably it's another reason. So one copy looks like the usual gamma function equation, but now you have like two independent copies. So it's like gamma in two directions. Okay. I shouldn't use C. Maybe I use W. Yeah, so W is like e to the pi. Yeah, probably that is better. Okay. So now we know the functional equation. We can have some properties. I shouldn't use it. And to answer the poll question. So the first one is that we have the following reflection formula that allows you to do some explicit calculation and special values. So we have this kind of important functional equation, and the proof is really just by calculating the definition, which I just erased. I shouldn't erase that. So if you do minus C, then in the expression that I just erased, it has this following form. The contour go this way. So it's the amounts to just playing around with change of variables. So for example, I change x to minus x, then the contour will go this way. And the term above has a minus sign. These are the same. And I can flip the minus sign. So I just flip the minus sign, which means I change the direction of the contour. So you can see that now I have the original expression, except that my contour go downward instead of upward. So to recover the original one, I have to move the contour from here to here, which means it has to pass through a pole. So the result is that if I go back to the original contour, I pick up a residue of the pole. And this pole is a triple zero. Yeah, I have 3 zeros downstairs. So you really have to expand the power series of 1 over sine h to get to the residue. So it's like the residue at x equals 0 times 2 pi I plus the original thing. So this is the phi b. And we just have to calculate what is the residue at x equals 0. And which is this thing, the triple thing. And yeah, and you can calculate this like b to the 4. Yeah, just expand the power series. Yeah. So if you put this term back here and then exponentiate, you get this funny constant here. Yeah, so as a consequence of this reflection formula, you can see, for example, that phi b of 0 can be evaluated explicitly. It is just that term. Square, yes, square. Just like that. And also important to us will be this number, b minus b inverse. So this is also non-zero. And so you can show this is also non-zero by the functional equation. The square is given by minus I b squared like this. So you combine the functional equation there with the reflection formula, you can also arrive at these values. And so phi 0 and phi of this equals the square root of these two numbers. But how do we determine the sign of the square root? Well, one idea is that you can look at the ratio of psi, right? So, for example, phi b of 0 will be plus minus that. And so which one is the correct one? Well, we can write this in terms of psi provided that b is imaginary square is bigger than 0, because both sides are analytic in B. So as long as I can compute the value here with one single B, then I can say that discrete choice. So I can say which one it is. Yeah, and you can compute this, and this is just one. Sorry, this is not one. This is some product, but if you set B to be square root of I, then this becomes 1. Yeah, so the plus sign is the correct plus sign is not the correct choice. It's plus sign is the correct choice. Yeah. So we have this one, and you can similarly do the top line. So phi b of this will be this number. And yeah, so in the literature, sometimes they will call this constant the theta b. A shorthand notation for this constant again, which appears often and often. So now I can discuss the poles and zeros that was asked. That's more important. So this function will have simple zeros at the positive linear combination after CB. Equals. And simple poles yeah. So it uses the fact that B minus B inverse is non-zero. So for example, I can check that CB using the functional equation. So I use the functional equation over on the left-hand side. So this is like CB minus B inverse. So I'm using CB minus B inverse. I'm using this line to get this, and we have shown that this is non-zero, and this is just 1 minus 1 if you compute out. So it is 0. So once you know phi CB is 0, then the rest is also 0 by the functional equation. And using the reflection formula I just erased, you can show that minus CB is a pole, and then all the combination will be poles also. And from this, you can also calculate the residues of the poles and 0. For example, yeah, I should use a reflection formula. So for example, the residue at this will be this number. Theta b is the theta b algorithm. Basically because of this number, which we know is like minus I theta b. You divide by 1/2I. So here I will to slip in some remarks. So phi b has these analytic properties, but then different literature, different context has different change of variables each to make things simpler to calculate. For example, when I first learned about the undialog, I learned it through Teschner's work, and Teschner used this version that I kind of use a lot in my work. So he first used a double sign. So it is defined as some change of variables and modification of the function. So he uses this form. So Q here is just b plus b. Or if you want, it's like minus I CB, 2I. Yeah, so this is the form he introduced. And the good thing about this is that the reflection formula, basically the choice of this part cancels with that funny term. So the reflection formula is particularly nice. It's just this. Yeah, so now the choice make it clear that there's nothing here. And the unitary condition is kind of shifted to the complex direction. So along Q over 2 real part, along that line, the function will be unitary. Instead of the original one, phi b, phi z is unitary along the real axis. So he shift to here, which is somehow motivated from Plancharo's, Mellin transform in functional analysis. And so as a remark to last class, we have exactly the relationship between this and the double gamma function. So I'm not going to prove this, but I'll just write down the definition. So Barnes' double gamma function is defined as the logarithmic derivative of the double summation So this thing is understood as some theta function, double theta function in terms of S. So of course, this does not make sense when t is negative or something, but you take analytic continuation of this as a function, as a complex function in both S and T. You differentiate t at t equals 0. You get a function in S, which is this. So that's the Barnes double gamma function. Barnes double gamma function with 2 parameters. And then Shintani's double sign function is defined as the BB inverse case. So that's how it is related to the old literatures in analytic number theory. So this is a remark. I'm not going to prove this. And also other variation that I like is the GB function. So this plays more of the role of the gamma function. So this time you don't have the exponential thing. So I'm going to discuss a little bit about this later, but this also Teschner's versions. So just different purpose have different variations. And since we have complex functions, then we should talk about asymptotics. So again, we look at the situation when z goes to infinity. And it's better summarized in a graph. So you basically have the complex B. So B is complex. So it has an argument. So let's say this is the argument of B. Counting from the imaginary axis for some reason. I draw the. So you basically split your complex plane into 4 parts. The function will looks like just the constant one along this region. So along this region. And on the right side, it will look like a fluctuating thing. Which is the term appearing in the reflection formula. So on both up and down, you will get an asymptotic that looks like the classical, not the compact version. So it looks like this thing, and it looks like the dual version. Yeah, so basically the asymptotic behavior of the function splits into 4 different situations. Yeah, so that's the thing. One time. Okay, so now here comes the most important part of today's lecture, is that this function satisfies a very. I'm ready to show that. I mean, I'm considering the whole region, and similarly for the other 4. So I have 4 regions. Yeah. Sorry. Is this the region? So. Oh, the Stokes phenomenon thing. I'm not sure. Yeah, I mean, along the boundary, they share simultaneously kind of both asymptotics. Yeah, I'm not sure. Sorry. Right. So the main properties that the complex or non-compact dilogarithm satisfies is the integral Ramanujan identity, or as we know it now, the Pentagon identity, the Pentagon relation, sometimes called 2-3 relations, or Teschner called it beta tau integral. So there are different names, but as you can tell from the name, it really is an incarnation of the Pentagon identity. So the proof I'll skip, but again, it's just hardcore residue theorem. So you have this funny term. Right. So we have five, so 5 terms. So it's a 5-term relation. And just to make sure this is not really algebra, it should be a contour. Let me just write a contour. It's a contour integral, and this contour has to go through the poles of both things. So this thing has a pole, 1 over this thing also has a pole, and the poles are appearing in like downstairs and upstairs. So your contour should avoid these poles. So these are the poles from x plus u, and this is poles from x plus 3. Yeah, and also in order for this to converge, I mean, they have the asymptotic behavior written over there, and one can compute or give a condition when this thing can converge. So my student provide me with this. These conditions. So as long as you have these conditions, then two things. Then first of all, this integral converge. So it makes sense to talk about function. And also, when you do the residue theorem of this part, you have to encircle like this big semicircle. And this condition ensures also that the big semicircle goes to 0. And this is not done in the literature at all. And we actually do some numerical calculations. And if you just don't have these conditions, you cannot apply the residue theorem actually. So the result might not be the same. Yes, there's a reason why it's called Ramanujan identity, but it's not the integral version. It's the hypergeometric series version. I wanted to skip that, but since you mentioned, I mean, just write down. So Ramanujan provides identity for this function. So it's the sorry. It's a double infinite sum. So kind of mimicking the left-hand side. And this can be evaluated explicitly. And then sometimes in terms of the theta function. So theta function is the standard theta function. Minus. Yeah, so I mean this is from Kashaev's paper. So this side looks like the left-hand side. These 3 terms looks like the thing from the right-hand side, and some residue terms. So that's yeah, like this AX corresponds to like WU on the residue term. Yeah, that's what this is the Ramanujan sum. So Kashaev called this relation the integral Ramanujan identity. And there are some special cases. The most useful one is the Fourier transform. So it's actually very interesting is that if you integrate, if you do a Fourier transform of your quantum dialog, again, you have to make sure that your contour passes through appropriate poles. Then this can be evaluated again to a quantum dialog. And similarly, the inverse version also. So, and this follows from the Ramanujan's identity as follows. So if I give a name, maybe. So if I give this a name, say UVW, then this really is the same as taking the limit of 0 to minus it. And this is yeah, so this is the thing. Yeah, I don't think I have enough time to complete what I prepared. But let me mention the asymptotics. I mean the version using Teschner's function, which, as I said, is sometimes natural. So if I rewrite the integration using the G version, then everything just cancels quite nicely. And you can see this is why Teschner calls the beta tau integration. Tau refers to the tau variables, but this is like a beta, it looks like a beta integral, like gamma alpha, gamma beta, and things. And also, he introduced a further function that we'll be using next class. So you take the principal log, then, well, I mean, or if you want, you can rewrite this as this. That. And it satisfies basically the relationship of psi, because yeah, it's really like the psi, the compact version, but taking into account both values. And if we do that, then the Fourier transform can be written this way. And the other version will be the G. And we'll be using this to discuss the operator version next class. Right, so I have no more minutes left. But I probably want to finish one more remark. So we talk about the function as Q is norm 1, but then of course a very interesting question is whether what happens if this is a root of unity. So there are probably several talks later that talks about this, and the result, at least in my notation, is the following. In fact, you have a closed form expression. So let's say Q is a root of unity, I over n, and here my B is m over n, and here my B is m over n, my S is mn. Then you can actually find an explicit closed form expression in terms of the classical dialogue. where the D function is known as the cyclic dialog, but it is really just a finite product. So this is the cyclic dialog, and it will probably be mentioned in some talks later. So in particular, when n and m is 1, we have an explicit relationship between the dialog and the quantum dialog. And you can also play around with some special cases. Right, so I want to show the slide also. Just for a few moments. So very quick view. Yeah. So this is the poles and zeros that I want to show. So B, just take a random complex B with positive real parts. Then the poles will, the zeros will be on top of the complex plane, and the poles will be on the bottom of the complex plane. And if you overlay this with the graph of complex quantum dialog, this is how it looks like. So this is a kind of general way to visualize complex functions. So the brightness of the graph shows how big the magnitude is. So black means very small, close to 0. White means very big, 100, 1,000. The color shows the angle or the phase of the complex numbers. So in particular, we have shown the asymptotics that on this region, the function tends to 1. So this red color is, when red is like the beginning color is 0, right? So this is the constant one. This is the e to the pi I c squared. So it can oscillate up and down. And the bottom and up will look like the classical dialog. So these are the poles, and you can see the bright spot. The bright spot corresponds to poles because the red is very big. And Teschner's version basically is just a 90-degree rotation of the previous graph. And also the center lies in like this Q over 2 instead of the axis. So it's kind of shifted a little bit. But the more important one appearing in operators theory later is the one when B is real, so that things becomes horizontal. The two regions kind of collapse into just, the four regions collapse into like only two regions. So the constant region and the fluctuating region. Yeah, so that's yeah, and final graph is the asymptotic behavior. So the compact dialog, okay, and the classical dialog, we know asymptotically this tends to that, and these two are not copy and paste. They are different graphs, but you can see, yeah, indeed, this is the asymptotics. Yeah, so I'll end here.